Imagine laying out several overlapping rectangular rugs on a hardwood floor. If you look closely at this arrangement, you'll notice one smaller rug is completely swallowed by the borders of a massive one underneath it. Visually, the small rug becomes completely irrelevant to the total floor space covered. We can translate this physical overlap directly onto a one-dimensional math timeline. Here, we plot out three specific intervals using their start and end coordinates. By dropping vertical boundaries from the widest interval, the mathematical rule for a covered interval becomes perfectly clear. An interval is completely covered if it starts precisely at or after a larger interval's starting point and ends at or before that same interval's ending point. Our final objective for this algorithm is simple. Sift through the entire dataset, eliminate the hidden intervals, and return the exact count of the ones that survive. The core challenge is efficiency. We can easily identify hidden intervals by hand in small batches, but we have to find a way to process massive amounts of data without endlessly comparing every single pair of intervals against each other. Attempting a brute force approach on an unsorted dataset generates a massive web of repeated calculations, representing an explosive O of n squared time complexity. But watch what happens when we sort these intervals by their leftmost starting coordinates. They snap into a clean staircase formation. Look at the math of this new structure. Because we sorted them, we now guarantee that every interval we check moving forward starts at or after our current position. We have instantly satisfied the first half of the coverage equation. By pre-sorting the data, we eliminate the need for multi-directional comparisons. The chaos is gone. We only sweep through the data in one direction. To track progress, we introduce a variable called maxEnd. This glowing vertical line casts a shadow, recording our furthest rightward reach. Stepping down, the next interval's right edge falls entirely behind this line. It is swallowed by the shadow and definitively covered. Look closely at this edge case, two intervals sharing the exact same starting coordinate. If we process the shorter interval first, it sets a weak maxEnd shadow at 4. The larger interval extends past it. Both survive, missing that the smaller one should be eliminated. How do we break the tie between identical start times to guarantee our shadow logic never fails? We introduce a secondary sorting rule. When start times are equal, we sort by end time in descending order. The longest interval must go first to cast the widest possible shadow, trapping the smaller intervals perfectly. Ascending start times combined with descending end time tiebreakers. This precise combination creates a flawless environment where checking a single variable is 100% accurate. Let's watch this optimized logic in action. As the sweep moves left to right across a fresh, properly sorted array, the maxEnd shadow efficiently consumes every covered interval without a single backward glance. This visual maps directly to the code. On the right, the custom comparator executes our two sorting rules, ascending starts and descending ends for ties. Then we establish our maxEnd variable and a survivor counter. We iterate through the array. If an interval pushes past our shadow, we increment the counter and expand maxEnd. If it falls behind the shadow, we simply skip it. Because we rely entirely on that initial organization step, our time complexity is O of n log n. The actual sweep is a highly efficient O of n pass, and because we only track a few variables, our space complexity remains O of 1. Sort the starts ascending, sort the tied ends descending, track the furthest shadow, and count what survives.
Let's walk through the solution. First, we're going to sort the n time ties 2 array. If the first elements of the two subarrays are not equal, then we're going to sort the subarrays in ascending order based only on their first element, without considering the second element. However, if the first elements are equal, then we are going to sort the second element in descending order, since the first elements are the same for both. Next, we are going to initialize two variables, count with 0 and end with 90s 1. Then inside the for loop, we access each subarray one by one. We check whether the current interval's ending value, which is the second element, is greater than the previous end. If it is, we increment count and update end to the current ending value. Otherwise, we skip that interval and move on to the next one. Finally, we return the value of count.